Welcome. In this session, we will see how we can reformulate the chain rule in terms of differentials. We will make use of this in our discussion of the substitution method for finding antiderivatives. In fact, we can rewrite all the rules of differentiation in terms of differentials. This has some advantages. For one thing, it turns out that in terms of differentials, the rules work somewhat the same way for both derivatives of functions of a single variable and several variables, and so on. We are going to make use of the connection between differentials and differentiation only for the method of substitution. This comes from the fact that when restated in terms of differentials, the chain rule looks just like substitution in algebra. Once again, it's easiest to explain using an example. So we look at the differential of the function given by e to the u, where u is 2x plus 1 power 3. Note that this is really a composition of two functions. If I substitute for u in e to the u, I can think of y as a function of x. Let's ignore that for the moment, just calculate the differentials based on our definition. U is 2x plus 1 quantity to the power 3. So by applying the power rule, we see that du over dx is 3 times 2x plus 1 power 2 times 2. So du is 3 times 2x plus 1 power 2 times 2 dx. Y is e to the u, so dy is e to the u du. If I substitute 2x plus 1 power 3 for u, and the differential we just found for du, we get e to the power 2x plus 1 power 3 times the quantity 3 2x plus 1 power 2 times 2 dx for dy. Now, if I had written y in terms of x, y would be e to the power 2x plus 1 power 3. And if I differentiate that using chain rule, I get the exponential times derivative of the exponent. So I get e to the power 2x plus 1 power 3 times 3 2x plus 1 power 2 times 2. And this derivative is precisely the expression here for dy. So basically we have written the chain rule in as a substitution. And as I said, we'll make use of this while discussing the method of substitution for finding antiderivatives.